Okay. Now we will discuss. We will do some problems based on the this linear transformation, right? Uh, for the first question, we will discuss about the isomomism, right? The linear transformation is isomomism. Then you can say that T is 1 to 1 and onto the linear mapping T is 1 to 1 and onto. This example based on the isomomism, right? You know the direct sum, right? We this formula here we prove the direct sum condition, right? Exercise number 1. Suppose that T B2W B uh, is an isomomism, is an isomomism, right? And that V equal V1 direct sum of V2, right? V1 direct sum of V2, so that this W equal direct sum of T of V1 direct sum of T of V2, okay? T of V2. You already know that here what is the thing you want to show that for this part, right? You want to show that there are two concerns you want to show that, right? There are two claims there. Claim for this question, you want to show that first condition and second condition, right? First condition, yeah, second condition. For a first condition, right? For a first condition, you want to show that you can take one of the element from this set W. That means small w belong to capital W equal T of V1, one of the element capital V1 plus T of V2, this small V2 belong to capital V2. And also you want to show that T of, right, T of this V1 intersection T of V2, right, singleton 0. Then you can say that W equal direct sum of T of V1, direct sum of T of V2. Okay. These two parts you want to prove for this question. Okay. Suppose that T V2W is a isomomism. Suppose T is an isomomism means T is linear mapping and T is 1 to 1 and onto. Therefore, we want to use these factors to prove this statement. Okay. Now, first, let you take one of the arbitrary element W belong to capital W. W belong to capital W as T is isomomism. T is isomomism means it is must be, therefore T is on true. Okay, T is isomomism means T is on true. Then you know that T mapping from B to W, we found one of the element W belong to capital W. There exists B belong to capital V such that this T of V equal W because T is on true. Okay, T is on true. This small w belong to capital W. That now you V equal V1 plus V2, where V1 belong to V1 small V1 belong to capital V1, small V2 belong to capital V2. Okay. but now wait, now how just wait, now now you can take told you that V1 belong to capital V1 and V2 belong to capital V2. Then we have here V equal to direct sum of V1 plus, V equal to direct sum of V1 direct sum of V2. Therefore, you can write here this V equal small v1 plus small v2. Okay, now you here t is linear now, then you take here t of v equal t of v1 plus v2. T is linear, then you can write t of v1 plus t of v2. Okay. But t of v equal to w, therefore w equal t of v1 plus t of v2. Here v1 belong to capital V1, v2 belong to capital V2. Therefore our first claim is, we prove now first claim, right? W equal to t of v1 plus t of v2. Okay, t of v1 plus t of v2. Now we move to the second claim. Second claim, we want to show that the intersection of t of v1 intersection of t of v2 is singleton 0. Okay, therefore let you take one of the element, let you take y belong to t of v1 intersection t of v2. Okay, therefore this one implies y belong to t of v1 and y belong to t of v2. Okay, y belong to t of v2. That is, the Rx is this b1 belong to b such that t of v1 equal y, and the Rx is v2 belong to capital V2 such that t of small v2 equal to y. Okay, t of small v2 equal to y. From which both, right? From this both, you can write t of v1 equal t of v2 because why but t is an isomorphism. Okay, t is an isomorphism. T is an isomorphism, therefore t is 1 to 1. T is 1 to 1 means v1 equal to v2. But we have the condition v equal to direct sum of v1, v2. Right? Now v1, v2 are equal. Right? v1, v2 are equal. But v1 direct sum of v2 singleton 0. Both are equal means v1 singleton 0. That means v1 0 and also similarly v2 also 0. Okay, v1 0, similarly v2 also 0. Take the one of the element as 0. Okay, v1 0 and v2 also 0. Suppose v1 0, v2 0 means y equal t of, here y equal t of v1. v1 0 no? T of 0. Right. T of 0, but this 0 belong to v. 0 v equal to 0 double g. Therefore y also 0. That means this intersection element should be 0. Y is 0. Y is 0 means, right? Therefore t of v1 intersection t of v2, this intersection element should be 0, belong to v 0 double g. Therefore the intersection element should be 0. Here 0 w. This 0 is in w. This 0 is in w. You can identify this one. W. 0 v means here the 0. Okay. Therefore direct sum condition also okay. First condition okay. Rho equal t of v1 plus t of v2. It is the direct sum condition. Both conditions are satisfying. Therefore, right? Therefore, this W equal t of v1 direct sum of t of v2. W equal t of v1 direct sum of T of B2. Okay. Okay, now we do this question. We'll do this question. let u, v, comma w be finite dimensional spaces, be finite dimensional spaces, and let S be one of the mapping v to w, and T another mapping u to v, be linear mapping, be linear. Prove that if S is 1 to 1, then your rank of ST, then rank of ST equal rank of T. Okay, rank of ST equal rank of T. Okay, U, V, W, B finite dimensional spaces, and S, B to W and T, U to V be linear. Prove that S is 1 to 1, then rank of ST, combustion function rank of ST is equal to rank of T. Okay, rank of ST equal rank of T. Let X belong to kernel of T. You take X belong to kernel of T. Then your T of X equal to 0, V. Now you take both side X function T of X. It is a combustion function T of X. That means S into T of X equal to 0, V. Here 0, V means here function assigned to here W. Therefore 0, W. Right? This function is ST of X equals 0, W means this X belong to kernel of ST. Okay, S belong to kernel of ST. Therefore, this kernel of T subset of kernel of ST. First condition. Kernel of T subset of kernel of ST. Okay. Now you take let X belong to kernel of ST. Now our claim is I want to prove this kernel T equal to kernel of ST. Then using the triangularity theorem, then you can prove this rank of ST equal rank of T. First claim is you want to show that kernel T equal to kernel of ST, right? Let kernel of X belong to kernel of ST means, right? S belong to kernel of ST. Therefore, ST of X equal to 0, double G. From this one, you can write S of T of X, this one, 0, double G. Therefore, this T of X belong to kernel of S. Okay, kernel of S. But you have the condition S is 1 to 1 if and only if this kernel of S equal to singleton 0. Therefore, this one is singleton 0 means T of X take the only values, right? 0, which function? Kernel of S here, no? In the V. Therefore, 0, V. Okay, 0, V. Therefore, from this part, T of X equals 0, V means X belong to kernel of T. You assume that X belong to kernel of ST. Now you prove X belong to kernel of T. Therefore, kernel of ST subset of kernel of T. Okay, it is your second condition. And 1 and 2, there are two conditions there. 1 and 2 implies this kernel of ST equal kernel of T. Okay, kernel of ST equal kernel of T. Now we use the rank, right? Rank nullity theorem here. Okay, rank nullity theorem here. The rank, by using the rank nullity theorem, by using the rank nullity theorem. Okay, dimension of U, right? Rank nullity theorem for right, ST mapping. Okay, what is the ST mapping? ST mapping range, ST, T range U, no, U V W, U to W, no, U to W. Therefore, dimension U equal okay, dimension U equal kernel of ST, image mean range. That means rank of ST, no? Rank means image of ST. Now, also for a S function you have T function you to have UTB, no? T function you have UTB. Therefore, also you can again write the dimension theorem for this part. T mapping here, ST mapping here. T mapping dimension U equal kernel of T plus rank of T. But you prove kernel of ST equal kernel of T. Therefore, this one equal to this one, this one equal to this one, therefore this one equal to this one. Therefore, 1 and 2 implies, 3 and 4 implies, 3 and 4 implies this rank of ST equal rank of T. Right? Rank of ST equal rank of T. Okay, right. Now, we will do this problem. Okay. Now, this exercise 3, assume that T be a linear mapping V to V. Recall that T squared denote the composition function, no? T squared denotes the composition, right? The composition T. Okay, T composition T mapping. T squared denote the T composition T mapping. Okay. There are some questions based on this part. For A part question, give an example of a vector space V and the linear operator T and the linear operator T belong to linear operator, okay? T is a linear operator V to B such that T squared equal T, right? T squared equal T, but not T take the value 1 or 0, but not take the value 1 or 0. B part, okay? Give an example of a vector space B and a linear operator T such that this condition. You want to give the example for this part, right? For this condition, you want to give the example. T squared equal T condition, you want to give the one of the example, right? But T not take the value 1 or 0, okay? B part, prove that if T squared equal T, then you want to prove that B equal null of T direct sum of null of T minus I. Okay, null of T minus I. Third part, prove that B equal null of T direct sum of null of T minus I, then you want to prove it T squared equal T. T squared equal T. This converse part for this part to this one. Okay. D part. Given example. Given example of a vector space V. Of a vector space V. Of a vector space V and a linear operator T. And a linear operator T. T belong to LB, B to B, right? T belong to LB, B to B, such that for this condition you want to give the example, T squared equal minus I. For this condition you want to give the example, like a first part, right? T squared equal minus I. Okay, T squared equal minus I. Okay. Right, we will do this problem now. First part, for example, you want to keep it for this part. Give an example of the vector space V and a linear operator T V to V such that this condition you want to satisfy. T squared equal to T. Okay, T does not take the value 1 or 0. Let B equal to R squared, no? Yeah, B equal R squared. Case, okay. You can find any example. Now we take B equal to R squared case and B vector space no R squared triple 2 and let T be linear. T be the linear. Okay, T be the linear map, right? Given by this one, T of S comma Y equal X plus Y 0. Then you take this example, right? T of xy equal to x plus y 0. Now you want to show that T squared equal to T. That is your claim. T squared xy means, right? T squared xy means T into T of xy. But T of xy means here x plus y 0. Now x plus y 0. Therefore, T of xy, this formula, therefore T of x plus y 0 means again x plus y 0. This is the thing S comma y, right? x comma y. That means t squared equal t for all s comma y belong to r squared. Therefore, now we prove that t squared to t, keep example this one, right? It is obviously linear one, no? It is obviously linear one, and you want to show that t squared equal to t. Here we consider vector space V equal to R squared, right? You can give any example, no problem here, right? V equal example of vector space B, right? V equal R squared. We give the example of R squared. You can give the example for R cube, right? Okay. Now for a second part, B part. B part, if t squared equal t, then you want to prove that B equal right sum of null of t plus null of t minus I. Okay, null of t plus null of t minus I. Okay. What is the form of null of t minus I? Equal, you can take any values b, right? T minus I, v equals 0. But it is null of t. Therefore, t minus I, b equals 0 function, then you can take t of b minus I of b equals 0. I of b means identity function. Therefore, t of b minus b equals 0. Okay, this one means t of b equal b. T of b equal to b, right? Therefore, right, we drive this part, right? We drive this part, we get a set of null space set, right? Null of t minus I, what is the set? We won't write that set first. We won't write that set first. The set first. Null of t minus I, no? Set of b, elements b belong to b. Here you drive t minus ib equal to 0, then you drive this one, tb equal to b. Okay, tb equal to b, right? Let you take the small b belonged in let b. Okay, we need to show that okay, we need to show that, right? If you take n belong to null of t, right? N belong to null of t. If n belong to null of t and u belong to null of t minus I, right? Null of t minus I, such that, what's the thing you want to show that? You know, here they asked to prove that b equal to null of t plus null of the right sum of null of t plus null of t and null of t minus I, no? Then you want to take here one of the element, here one of the element. You want to show that such that here u, no, sorry, b equal to n plus u. B equal to n plus u. Since, right, okay, since suppose t of b equal t of b, no? Because here t of b equal to b. Suppose you take t of b, again t of b equal to b, no? Therefore t of b. Therefore, suppose this condition satisfying, then it is this t of b belong to null of t minus I. Because this condition satisfying t of something here, again that something, therefore this one t of b belong to null of t minus I. Okay, null of t minus I. Consider this part. Consider this t of b minus b, right? T of b minus b. Okay, t of b minus b. t of b minus b. Now you take t b minus b both side, then you get t squared b minus t of b. But you already have t squared equal to t, no? Therefore, t of b minus t of b. This one 0. This one 0 means this t of b minus b belong to null of t. Null of t. Okay? Null of t. Now you write b equal to tb minus b plus b, no? Is it okay? Sorry. B plus t of b. Okay. Okay. And now, okay. Here, t of b minus b, right? T of b minus b, right? Okay. Okay. Now, t of b minus b belong to null of t. This null of t, which is t of b means here. T of b. This one null, t of b means null of t minus I. Therefore, this one you can write, no? V equal to this one. Here t b belong to null of t minus I, and tb minus b belong to null of t. Yeah, tb minus b belong to null of t, right? This one null of belong to null of t. This one belong to null of t minus I, right? Therefore, b belong to capital B. Therefore, this b, I think b belong to. You can write null of t minus I plus this tb belong to tb minus b belong to null of t, no? That one here. This one null of t. This one belong to null of t. This one belong to null of t minus I, right? Therefore, right? Therefore, b belong to okay. For a set, therefore b belong to b, no? Therefore, b subset of null of t plus null of t minus I. First one, right? Null of t plus null of t minus I. Obviously, right? Obviously, this one condition satisfying. That means this null of t plus null of t minus I subset of b, no? Subset of b. Because here null of t minus I b, that means b belong to b. This one b belong to b. But null of t, right? Null of t means b mapping from LB, no? That means b, t mapping from b to b. T mapping from b to b. Therefore, this null of t also subset of b. Therefore, null of t plus null of t minus I also subset of b. Right? Is clearly true. Okay. Second one, 1 and 2 implies b equal null of t plus null of t minus I. Now, you want to show that the intersection element, no? Now your claim is this one. Now you want to show that your claim is this null of t intersection null of t minus I singleton 0, right? Singleton 0. For direct sum condition, for a second claim, you want to prove that this condition, right? Let you take one of the element from the set. Let B belong to null of T intersection null of T minus I. Okay. Therefore, B belong to null of T and B belong to null of T minus I. Small b, no? Small b. Okay. Now, B belong to null T means T of B equal to 0. But you already have T of B equal to B, no? Therefore, B 0. And B equal to null T minus I means T minus I B equals 0. Therefore, TB minus IB equals 0. I is identity mapping, TB minus B equals 0. TB equal to B, but B 0. Therefore, TB also 0. Therefore, this case B is 0, no? B is 0 mean here you take B, no? This B is 0. Therefore, this null of T intersection, null of T minus I, it is singleton 0, no? Singleton 0. Therefore, this both conditions are satisfying. You put here this star, here another condition, another double star, and this 2, you can write, therefore, star and double star implies B equal to null of T direct sum of null of T minus I. Okay, null of T direct sum of null of T minus I. Okay. Now, reverse part. Suppose this condition satisfying, you want to show that T squared equal T. Okay. Okay, now we will try to this part. This is your C part. That is your C part. For a C part, you want to show that T squared equal T, but this condition is satisfying now. B equal null T plus null of T minus I. Let you take one of the element B belong to capital B. Since we have B equal null of T, B equal null of T plus null of T minus I. Now, therefore, you take N belong to null of T and U belong to null of T minus I, then you get such that you get B equal N plus U. By the some condition, you get this one, N plus U. Then you take the linear both side, TV, Tn plus U. Okay, Tn plus U. This one Tn plus Tu. But N belong to null of T means Tn 0. But T of U means, right, T of U already defined, previous part, T of U equal to U, no? T of U equal to U. Therefore, this one U. T of B equal to U. Therefore, this T of B equal to U, and since we showed above already solved this condition, no? That U belong to null of T minus I. In the previous part, we showed this one. U belong to null of T minus I. Okay. But U belong to null of T minus I means T of U equal to U. Okay. T of U equal to U. Therefore, you take both sides T squared B equal T of U. Okay. T squared B equal T of U again U. This means T squared B equal U. Okay. T squared B equal to U. But you already know that this U equal to, right, U equal to T of B. Right. Now for all B belong to B, T squared equal T. Right. From this part, T squared equal T for all B belong to capital B. Right. T squared equal T for all B belong to capital B. Okay. On that part, okay. Now D part. Now your D part. Now your D part. Let here also you take B equal to R squared. You want to keep the example, no? R squared. And you take and let T be a linear mapping B to V. be defined by t of s comma y equal y comma minus x. Okay, y comma minus x. Now you want to show that t squared equal minus I. That's all. T squared s comma y equal t of xy. But t of xy means y minus x, right? Therefore, you put here minus x y. So minus x minus y. Okay, minus x minus y. Okay, then you can take minus outside s comma y. This means t squared sy. This one you can write t squared xy I of xy. You put here minus first. Therefore, your t squared equal minus I. Okay, t squared equal minus I. Okay, t squared equal minus I. It is the example for this t squared equal minus I. I times xy means xy again. Okay, I this identity mapping. Identity mapping is a linear one. Okay, this is these are the exercises based on the linear transformation. Okay, right.